Hi everyone, thanks for giving me this opportunity to talk to you guys about Scouter models. Let me start with an introduction. I am Kumaran Ponnambalam. I work at Cisco in the Cisco Outshift team. I've been in the AI data world for more than 20 years, and I'm author on LinkedIn Learning and a speaker in tech conferences. In terms of agenda, we are going to look at what model drift detection entails, what kind of challenges exist in detecting concept drift, and how this Scouter model can help in overcoming these challenges and some of the learnings in building Scouter models. So this is kind of a research that we did in terms of trying to predict model drift when true labels are not available. So let's begin with a little background on what is drift. Drift is essentially when the predictive accuracy of models in production, they reduce or decay over time. So for example, when you look at the graph on the right side, model 1 is decaying slowly, the blue line. Model 2 is like okay for some time and then decays abruptly, whereas model 3 is okay. So you could see all these kinds of patterns in production when they are running, and there could be many reasons why drift happens. One of the types of drift is what is called concept drift or model drift, where the relationship between the features and the target changes over time. So the original model that you built is no longer applicable. The second type of drift is feature or data drift, where the distribution of values for the features changes over time. Their mean or standard deviation changes, or new classes get introduced. So that could also impact how well the model performs in production. So ML models do need constant monitoring in production to detect drift and make sure that they are continuing to perform to expectations and delivering the results that are needed. And typically drift resolution means you're updating training data sets, retraining the model, or if there are any data issues, you also fix those issues. Moving on to what are the challenges in detecting concept drift. So we're going to focus on only concept drift here. So concept drift requires comparing the performance of the model during training with several time periods in production. So you're going to have the baseline set in training as to this is the performance of the model. Then you're making sure that the model continues to perform at the same level month after month or week after week. What you use to measure concept drift is you're looking at measures like accuracy, precision, recall, F1 scores. So when any of these measures fall below the thresholds that you have set, then it means that the model is drifting. But the key thing is that computing these measures, they require both the predicted label and the true label in production. So whenever you're doing some predictions in production, you also need the true label, and that's where the challenge exists, because true labels are not available in production data all the time. You're only predicting it, but you don't know what the true value is. Sometimes it's available, sometimes it's not. You can try to add true labels by like human labeling. That could be pretty expensive, especially for a large data set. You could use other generative methods like automated labeling kind of things, but that has also shown to be error prone. So how do we detect, how do you measure concept drift when true labels are not available in production, and that too in a quick and automated fashion? So that's when the Scouter model comes in. A Scouter model is a complementary model that is trained on the same training data as the main model. And it helps to predict if the main model is drifting in production. So it's built on the same training data, and it helps to predict if this main model is actually drifting in production. So how do we build the model? So we look at how do we build the model and use the model now. Let's take a small example. Let's say this is website visits data, which is like you're looking at data about users visiting your website and trying to predict if the user is going to buy a product. So you're looking at gender, age group, income, and visit duration as the features, and buy, yes or no, as the target. So these are like 4 feature variables and 1 target variable. And you will build your main model by the usual means that I believe everyone is familiar. Now, how does the Scouter model's training data looks like? When it comes to Scouter models, the target in the for the main model becomes a feature in the Scouter model. So we are making buy as a feature, and we are picking one of the features for the main model as the target. So we're kind of flipping there. the feature and target. So we're going to now use by with other features to predict the age group. So that's what the Scouter model is going to do. So that again, you're going to go through the regular model building process, train, test, verify, same process. Then we want to establish a relationship between the main model and the Scouter model. How do you do that is you create test data sets with simulated drift. How do you simulate drift is if you can introduce some randomness in the target in your training data set, various levels of randomness, so 5%, 10%, 15%, that will automatically create some drift for you. So create these data sets with simulated drift, and then you test that with the main model, you test that with the Scouter model. So you may, if you have like 20 data sets, then you observe for the main model and the Scouter model what accuracy it gives. And using this, you can actually a relationship between the Scouter model's accuracy and the main model's accuracy. So as you can see, this is here a very, a very good pattern that you see here. But it depends on the data set and use case. This pattern may vary. It may not be linear. It may be sometimes some polynomial, something like that. But if you can establish this relationship between what the Scouter model's accuracy is and the main model's accuracy is, and have a way of computing that, like in this case, you can do a linear regression and have the equation y equal to something, x plus something. So using the Scouter model's accuracy, you can then compute what the main model's accuracy would be. So once you have this Scouter model ready for training from the training, then you could then go and use it for detecting drift. And how do you do that? Is you start with the main model's production data. So you got 4 feature variables coming in there, and then you're going to use the main model that you have, and you're going to predict the by, the predicted by that is the predicted label for the main model. Then how do you get the Scouter's production data? Is you take the gender, income, and visit duration from the main features and use it for Scouter features. And then the predicted by from the main model becomes a feature for the Scouter model. So instead of using by, you're using predicted by, which is what the main model predicted in production. But you also see that you have age group already in production, so that actually becomes the Scouter's true label. So now you have the Scouter production data with which you can now predict age group. So you have the predicted age group and the true label age group, both are available for the Scouter model, with which you can compute Scouter's accuracy over time. So you can take different intervals and start computing the Scouter model's accuracy over time. Once you have the Scouter model accuracy, you already have the relationship with the main model's accuracy, so you can use that to compute the main model's accuracy. So even though you do not have the true label for by in production, you're using the Scouter model to kind of be a proxy of what the main model's accuracy is. This way you can compute the main model's accuracy, and this allows you to track the main model's drift over time. So this is the kind of sequence of steps that you would do to kind of go from the model training to using in production. So this is what you heard so far as the concept. It's like kind of an ideal concept. And how well will this perform? Is where we've done a few tests actually over different sets of training data, and some of our observations is something I want to share. The first observation is that we found that when we had multi-target, multi-class main targets and Scouter targets, it seems to give the best correlation, which is like it is a classification variable and it has 4 or 5 distinct values. So this yes or no doesn't work very well, but if you have like 4 or 5 values, both for the main target and the Scouter target, this scheme seems to work very well. We have seen that choosing a feature that has the best correlation with the target. So in the main model, choose a feature that has the best correlation with the target variable as your Scouter target. That also seems to give good performance in most of the cases. But it is also recommended that we experiment with all the features, because some of the features may not have that many classes. Some of them may be like yes or no kind of class, yes or no kind of classes only. So it depends on the variable. We are seeing that they give different kinds of results. So you are not going to see a really linear kind of relationship. It may be very spread out. It may be very random. So it also changes feature to feature. When we have binary targets, what we saw was that try converting these binary targets to multi-class targets. How do we convert that? As like usually when you see a model predicting yes or no, you go to like naive Bayes, it's going to usually give you a probability. So if you can use that to kind of split it up into something like strong by, weak by, strong no by, weak no by, so you kind of spread out the classes and then use them for the Scouter model, it seems to give us better results when we do these kind of Scouter models. And if it is continuous features, do binning, which is you convert them into bins of 4 or 5 unique bins. That also seems to give some really good results in this case. And the other things we also see is to try different algorithms for the Scouter. One main thing that we need to keep in mind is that to keep the Scouter's inference costs down, because this is just a monitoring model, you don't want this to be super expensive to build or maintain. Like you can go to neural networks and build really complex models, but is it worth the effort to do that for a Scouter? Because that's not your main model. So you need to keep your Scouter's cost down. So one is you can go for a lot more simpler algorithms. And second is you can also use sampling. Sampling is another option you can use. Like you don't have to do a Scouter on every single production instance, data instance that you're getting. Rather, you want to sample your production data and then run this monitoring only on that sample. So that's another thing that you can also do. So this is continuing research. We've looked at, to start with, classical machine learning. We're also looking at computer vision and NLP. In both cases, if it is still a classification problem, most of the concepts hold good. The problem is, there are too many number of features in computer vision and NLP. So computer vision, you can use dimensionality reduction to kind of reduce the number of features and try to predict that feature. When it comes to NLP, again, you can use the tokens as your features also. But again, it's pretty complex, so that's something that we try to do to bring it down. So those are this is kind of, as I said, research that we have been doing on various data sets, and that's pretty much what I want to share with you guys.